Okay, it's time to talk about the nitro group. Last time, we spent some time talking about how to install a nitro group. And we can do so by using sulfuric acid and nitric acid. And that puts a nitro group onto a benzene ring. Now, what can you do with the nitro group? Turns out you can convert this nitro group to lots of different groups. It's a very important intermediate, well, synthetic intermediate on the way to other things. Such as, well, you can take the nitro group and you can reduce it with hydrogen and palladium. And you can get an amine out of that. The mechanism's not one that we're going to go over. You don't need to know it. But we have other reduction schemes as well. So real quick, let's say we had this molecule right here. How would we make it? Well, both the carbonyl group and the nitro groups are meta-directors. So we can add the carbonyl group on first. Followed by the nitro group. Or we can add the nitro group on, followed by the carbonyl group. Aluminum chloride, acetyl chloride is just this right here. The acetyl group is this right here. Acetyl is just an abbreviation for this group. Although it looks good on paper that the two are interchangeable because they're both meta-directors, turns out the second case won't work because this is a Friedel-Crafts reaction. And Friedel-Crafts reactions do not work on strongly deactivated rings. And so if there's a meta-director on the ring, that means it's a strongly deactivated ring. The Friedel-Crafts reaction's not going to be able to work on it. So as a result, the bottom case scenario doesn't work. The first one does. Now, the reason I'm bringing this up has to do with reductions. Turns out hydrogen on palladium is pretty selective and doesn't react with carbonyls very quickly at all. As a result, you can selectively reduce the nitro group in the presence of a carbonyl. Now, If you do this with a hydride source, such as sodium borohydride, you can selectively reduce a ketone in the presence of a nitro group. LAH is pretty strong. And it will typically react with both. And so it's not a good idea to use LAH when you have a nitro group on there. And it typically gives a mess with partial reduction of that. Such as going just down to the dihydroxylamine. Into the amine, you get a mess. So don't use LAH. Other ways of reducing carbonyl we just recently covered the Clemenson conditions. Turns out the Clemenson conditions don't allow the nitro group to survive. And they will end up reducing both the ketone down to the alkane and the nitro group down to the amine. The Wolff-Kishner. If you're very careful and choose the correct Wolff-Kishner conditions, and we'll just use the standard Wolff-Kishner conditions as the correct conditions, you can actually get away with selectively reducing the carbonyl and leaving the nitro group in place. It's a tough one to do, but that's a common one. So just be careful on your choice of reduction conditions. The nitro group is a very reactive compound to reducing conditions. Other reducing agents to avoid, well, we've already talked about. Avoid using LAH with nitros. Also avoid using organolithiums and Grignards with nitros. Because these, organolithiums, Grignards, and LH, have a tendency to give messes / unpredictable results. So try to avoid that. Now, but the reduction of the amine is actually quite important. Because in 2 steps, we can put an amine directly onto a benzene ring. And then 2 steps later, we can convert this amine to a vast majority of things. Such as, well, one such reaction, it's a very important step, it's called diazotization. We take sodium nitrite and notice that it is NaNO2. That's different from the nitration conditions, which is NO3. But a solution of sodium nitrite in HCl can give what's referred to as a diazonium salt. And this reaction is called diazotization. Need a drink of Dr. Pepper after that word. Diazotization. I think I said that word about 7 times and didn't pronounce it the same way twice. Oh well. But it makes a diazonium salt. These things are unstable and should not be isolated. They tend to go boom. So you have to be very careful when you're working with a diazonium salt because they are ridiculously reactive. And with a lot of ridiculously reactive things, once you make it, you should use it right away. And what it can be used for? Well, it can be used for a reaction called the Sandmeyer reaction. Where we take this diazonium salt and react it with various copper salts, such as we can react it with copper cyanide, and we get a nitrile on the benzene ring. And this is the only way that we have to install a nitrile directly onto a benzene ring in this class. You could also add copper oxide, and all these reactions are done in water. If you don't include water, that's okay. But if you do it with copper oxide in water, you can replace the diazonium with an OH. And I've sort of rotated the molecules. So to kind of give you an idea a little bit better, I'm going to add a methyl group to each of these to show the relative position. The substitution occurs right on the carbon that the diazonium was on. Got another reaction for you. You can use copper chloride. That replaces it with Cl. copper bromide? Well, if you do it with that diazonium salt, you actually will end up getting a mixture. The bromide and the chloride. So you have to be a little bit careful when you're using the copper bromide salt. Where is this chloride coming from? Well, this chloride is coming from right here. And the Cl- came from the diazonium species, or the diazotization reaction, I should say. So if you want clean reaction with this, replace the bromine with copper bromide, you have to do a little bit planning ahead. What you have to do is take your amine and react it with sodium nitrite, NaNO2. Instead of HCl, use HBr. That gives the bromide salt of the diazonium. And then you can cleanly use copper bromide. If you don't include the water, that's fine. But of course, if you use this in copper chloride, you end up getting a mixture of the two again. So you really have to be careful when you're using copper bromide or copper chloride when you're replacing the diazonium. Okay. I've got two more reactions to show you of this diazonium salt, which are unique because they don't involve copper at all. You don't need copper to react with them. The first case is you can take potassium iodide, and turns out potassium iodide is reactive enough that it will displace the nitrogen on its own, and you don't need a copper source. And since you need a copper source with chloride and bromide, you don't have to worry about competing of these anions with iodide, because iodide just will outcompete them, because chloride and bromide both need a copper source. And the other reaction involves using H3PO2. H3PO2, well, that's what's called hypophosphorus acid. And hypophosphorus acid is actually a reducing agent. What it does is it will replace the diazonium with a hydrogen. Now, this might seem like it's not a big deal. It might even seem like a silly reaction given how many steps we do to put on that diazonium. But this is a way that we have to actually incorporate deuterium onto a benzene ring. It's not the only way, but it's a good way of doing it. Now, this is one of the few ways we have of putting a nitrile onto the ring. Also, it's one of the few ways we have to put an OH on the ring. It's also the only way we have to put an iodine onto the ring. But putting a chloride and a bromide onto the ring, we have other ways of doing it. So why is that so special? Well, think about it this way. The Sandmeyer sequence is the following. You nitrate. You reduce. You diazotize. And then you do the Sandmeyer reaction. That's a lot of steps to put a chlorine on when we've already have halogenation. So this first way is steppy. Second way is quite a bit more efficient. Second way is better. But here's the strength of the Sandmeyer reaction, of this whole diazotization process. The nitro group, keep in mind, is a meta-director that is then turned into an orthopara director. So, if we use the sequence one more time, nitration, adds a nitro group. Chlorination adds a chlorine. And since we have a meta-director on the ring already, adds a chlorine meta. Reduction. Followed by diazotization, and reaction with copper chloride. And these two convert the NH2 into a Cl. And what we've done is we now have two orthopara directors that are meta to each other. Now if you added just, say, chlorine, and then add it a second time, well, that's an orthopara director. You'd likely end up getting the two chlorines para to each other as opposed to meta. And so that's one of the strengths of using this sequence. And that's all I've got for today. And we will tune in next time. guess I only spent 25 minutes on this, so I went awfully fast. So when I go too fast, please pause. And you're thinking, I already do, or now you tell me. Well, we're learning as we go.